Alright, so since you're on a part 2 of this, I already apologize. The document camera seems to be giving me fits today. Not quite sure why, but I've already filled out most of the rest of the notes at this point and lectured for about another 15-20 minutes since this. So I'll be kind of talking through the things and they'll be filled out already. So if you need to pause so you can write things down, definitely feel free to do so. Alright, so we've been looking at this example 2, and we want to go ahead and estimate the instantaneous velocity from this example at time t equals 1. So what we're doing then for this instantaneous velocity is we're trying to go ahead and pick smaller and smaller intervals so that we can get to where we're going and get as close to 1 as humanly possible. So we're going to start off by just picking a point near 1, so 0.99 might be a good place to start, and try to find the average velocity there and see if we can make an educated guess. So if we're looking at the average velocity on 0.99 to 1 as our interval, h of 1 minus h of 0.99 over 1 minus 0.99 is going to be that formula. So remember, we're looking at our change in position over our change in time. So when we plug that in, we end up with 15 times 1 minus 4.9 times 1 squared minus this quantity in parentheses, all divided by 0.1, and we end up getting 5.249 meters per second. Now, if you think you know exactly what the instantaneous velocity should be at time t equals 1, I encourage you to write down a prediction now. However, this is not enough information for us to know exactly what the instantaneous velocity is going to be. It might be a decent guess, but we can do better. So we can pick a bunch of points to go ahead and do this with. So if we want to pick a bunch of points, instead of going ahead and plugging all the way in, what we might want to try doing is just seeing if there's an easier formula. So we always know we're going to be using 1, so if we tried to plug in from t equals, or for some value of t near 1 and 1, we'll always have this 1 as part of the formula. So plugging that in and plugging in t, we'll have h of 1 minus h of t over 1 minus t. So just again, following along with this formula from before. So this will be 15 times 1 minus 4.9 times 1 squared minus, and then in parentheses, 15t minus 4.9t squared divided by 1 minus t. And this gives us the following formula of 10.1 minus 15t plus 4.9t squared all over 1 minus t. So you might think to yourself, even though we've got this nice formula, it's still going to be a plug in a bunch of different values. I agree. So what we're going to do instead is we'll go ahead and use our calculator to do this. So if you have a graphing calculator, like I do, you can go ahead and pull it out and try to follow along with these ideas. So what we're going to start off with is we're going to go ahead and put in our function. So in the y equals menu, so I'll put out y equals, we'll type in our formula we just found for average velocity. So what we have here is we'll use parentheses to encapsulate the numerator and denominator. So we have 10.1 minus 15. Now I know it says t, but t is just a placeholder for the time variable. So we could use any variable. So we'll use x because that's kind of what is default on the calculator, plus 4.9 x squared, and then we will close the parentheses, and then we'll divide by, in parentheses again, 1 minus t. I know it says x on the calculator, but it's 1 minus t. It's just a placeholder variable. Okay, so now that we have this function here, we're going to go ahead and we're going to go to second window. So we can basically go ahead and it defaults to auto and tell it to ask us for what we'd like our values to be that we're plugging in for our independent variable. So we'll tell it to ask. Then we'll quit out of that. And then last, we'll go to second graph, and we can put in the x values we'd like, and it'll spit out the y values. So we can start off with our 0.99, and this will allow us to verify that we have 5.249 meters per second as the thing we're working with. Okay, so we can keep going and get closer. So 5.999 is a little bit closer. Okay, so we see what we get as our y value. Now it's 5.2049. And this might be enough for you to get the sense, but to really get a good practice for this, we're going to go ahead and plug in a few more values. So now we've got 0.9999, and it's getting closer and closer to 5.2. But that's only from one side. What if we wanted the other side? Well, let's go ahead and do 1.0001. All right, so now we're a little less than 5.2, but we're still around there. We can do 5.001, 5.01, and, or sorry, 1.01 and 1.001. And we see we're really close to this 5.2 on either side. So because as we get closer and closer to 5.2 as the intervals close around 1, what that implies to us is that the instantaneous velocity at x equals 1 is approximately 5.2 meters per second. So that's what we're going to go with for now for our answer. We'll get a more formal way of finding this instantaneous velocity sooner. Now, we had talked at the beginning that we're interested in rates of change. So not just for velocity, but we'd also be able to do it for a number of different types of rates of change. Well, it turns out that this idea, this formula, can be kind of extended for any type of function. So we're going to have a definition. Let y equals f of x be a function. Then the average rate of change, which I'm going to denote AROC, of f with respect to the interval x1 to x2 will be given by the change in f over the change in x. So delta f over delta x. This will just be our way of symbolically noting these ideas. So if you see that in the future, don't panic. It's doing this. And that's going to be f of x2 minus f of x1 over divided by x2 minus x1. And so what we've noticed is that the average rate of change converges to the instantaneous rate of change, IROC, as the x interval shrinks down. But this should remind you of a formula you've seen before. So if you're looking at delta f over delta x, essentially that's the same in delta y over delta x, which is just the rise over the run. So the average rate of change, in essence, is the slope of some line. What line, you ask? Well, we'll see that on the next page. Remember, you can pause the video if you need to go ahead and have a little bit more time to write things down. And normally you'd be able to keep pace with me, but again, this has been pseudo-recorded at this point. So I apologize for that. I have to figure out what's wrong with the camera, why it keeps breaking up these recordings. Okay, so that brings us then to the graphical interpretation of rates of change. So if we have a line connecting 2 points on a graph of a function, so these 2 points will be x1 f of x1 and x2 f of x2. This is going to be called the secant line between those 2 points. So if we want to find the average rate of change of a function on the interval -1 to 3, what we're going to be doing is we'll be looking at the x values. So -1 has a y value of, or f of x value of -3. So we have the point -1, -3, and the other endpoint is 3. So we'll be going 1, 2, 3, and going up, and get the point 3, 5. And so we're going to connect these to the secant line, and when we want the average rate of change between those values of -1 and 3, what we're looking at is the average rate of change being the same as the slope of this secant line. So finding that slope, we're going to have f of 3 minus f of -1 divided by 3 minus -1. And so we'll have 5 minus -3 divided by 3 minus -1. And so that goes a over 4, which is the rise over the run, which will be 2. Now we don't know what the units are for this f. Maybe it's velocity, maybe it's something else. So for now, the average rate of change is just 2. And so what that tells us then is that over this interval, on average, we're going up by a value of 2 as the x value increases. Now, the tangent line is the thing we're going to be most concerned about in this class. So the tangent line is the line that touches a curve f at a single point. So here, if we wanted to look at the tangent line at x equals 2, essentially we draw a line that only touches the curve at x equals 2 and nowhere else. So here, some examples. Say I've got a little curvy line. If I have a tangent line that touches just here, that's going to be a tangent line. But if I've got a line that connects 2 points, it'll be a secant line and not a tangent line. So as some examples, let's go ahead, or you should go ahead and try, before looking at this, no, you've seen it, don't remove it from your brain. Draw a secant line on the intervals for this function above for -2 to 2, 0 to 2, and 1 to 2. Okay, you've done it? Great. So remember, what we're doing is we're taking, for these different values, we're looking at the x values and picking the points associated with those x values and then drawing a line connecting those dots. Essentially, we're playing connect the dots. So here we've got something where we've got a slope of 0. It's just a horizontal line. As we look at 0 and 2, we've got a 0 here, 2 here. And connecting those dots gives us a more up and down line, kind of on a slant. And if we look at connecting between 1 and 2, we end up even more up and down. And what we should notice is that the closer we get to just having that interval be equal to, the closer our secant line is to just being our tangent line. So as our secant lines and our intervals are getting smaller, our secant lines get closer and closer to being that tangent line at x equals 2. So we're getting very close here. So that's exciting. So just as a little bit of a summary of what's going on graphically, as the intervals get smaller, our particular x value, the secant line will converge to the tangent line. Our average rate of change of a function f over the interval x1 to x2 is going to be the slope of the secant line through the points x1 f of x1 and x2 f of x2. So that's really easy to calculate. All we need are these 4 values, and then we know how to plug them into a formula. So that's not too bad. The instantaneous rate of change, on the other hand, is a function f at a particular point x of a function f at a particular point x1 is going to be the slope of the tangent line to f at that point. Now the problem here is that when we look at the slope of the tangent line, all we know is x1 f of x1. So remember, if you want to go ahead and find the slope of a line, you need to have 2 points to be looking at. So since we only have 1, finding the slope of that tangent line right now is only something we can approximate. So what I want you all to do is I want you to take a minute to try to do example 5 on your own. So it says the number p of t of E. coli cells at time t in hours in a petri dish is plotted below. So we've got this x-axis, t-axis, and y-axis, or p of t axis. Note the units, so this is 1, 2, 3, this is like 1,000, 2,000, and the solid lines are every 2,000. First thing you want to do is calculate the average rate of change of p of t from hour 1 to hour 3 and draw the corresponding secant line, and then interpret your answer. And then the second thing you want to do is estimate the slope of this line here on this graph, and then tell me what it represents. So take a moment, give it a shot, and then we'll go through it. Alright, so hopefully you paused the video and given it a shot. So let's look at part A. So part A, we want the average rate of change of P on the interval 1 to 3. So this will be P of 3 minus P of 1 all over 3 minus 1. So if we look at P of 3, here it looks like we have the point 3, 8,000, and here it looks like we have the point 1, 2,000. So then we'll take 8,000 minus 2,000 all over 3 minus 1 is 2. So we should get 6,000 over 2, or 3,000 cells per hour. Now, what does this mean? It means that on average, cells grow, the number of cells grows by 3,000 hour 1 and hour 3. So again, we want to make sure we can go ahead and draw this secant line. So we've got one of the points here, we've got the other point here, and we get to play a game of connect the dots. Okay, so that's going to be part A for us. So for part B, we want to go ahead and try to find a way to look at and estimate the slope of this line L. So what we need to figure out then is what we're kind of looking at, what it's representing here. Now normally we don't have a second point if we're trying to look at what we could assume is a tangent line. But right now we have this graph here, and we could try to look at one of the points to make some sort of estimate. So if we look at this point here, where we know it crosses 6,000, it's probably not exact, but it's probably approximately the point 3.56,000. So let's use that then for part B to make our best guess at what's going on. So for B, we're going to look at points 1, 2,000 and 3.5, 6,000. And so our slope of this line will be 6,000 minus 2,000 all over 3.5 minus 1. And we see that we should end up getting 1,600 cells per hour. So again, this is our best estimate because we don't actually have exact things on this graph. And so L appears to be our tangent line at t equals 1, and the slope of L is the instantaneous rate of change at t equals 1. Slightly off the slide here. All right, now if you're worried that instantaneous rate of change seems a little rickety right now because all we're doing is making our best guess as this line, or we're just trying to pick a bunch of points and approximate it, well, good news, you signed up for the right class. So starting next week, we're going to look at the idea of limits, and that will try to lead us then into the idea of figuring out exactly what this instantaneous rate of change is, as opposed to just making our best guess.